to the 9th lesson in area of study 3. Today we'll be having a look at the concept of mass energy. So what are we going to do? Well, we'll start off with a quick introduction to quantum physics. We'll then discuss and kind of have a look at what is mass energy. We'll have a look at Einstein's famous equation, particles and antiparticles, and then kind of an application of that in fusion reactions. We'll finish off with some relativistic momentum and relativistic mass, kinetic energy, and taking a look at some graphs. So, what is quantum physics? So, simply put, it's the study of really small stuff. So think about atoms and quarks and some of the things that you may have learned in physics 1 and 2. It kind of looks at what their behavior is. So it's a bit like the study of really small things and how they work. It became a field of science and physics in the early 20th century when we discovered the atom. So the atomic mass and mass defect. So these are important concepts when it comes to fusion reactions, and we'll have a look at that a little bit later on. But pretty much when a nuclear reaction occurs, there's a difference between the mass of the products and the mass of the reactants. 1 unit of atomic mass, which is given by the symbol U or AMU, meaning atomic mass units, equates to 1/12 of the mass of a carbon-12 atom. There is no specific reason that they chose that, other than it's quite an abundant material, carbon-12, so they chose a unit that related to that. And so 1 unit, so 1 U, is 1.6605 by 10 to the negative 27 kilograms. Now, you may have learnt this in physics 1-2, but not all schools do. So you may want to note this stuff down. Right, let's have a look at a deuterium-tritium fusion reaction. So it's got the following products and reactants, which we can see in that, I guess you could call it formula over there. And we've got the products. We've got 2 lots of, so we've got 1 lot of hydrogen-2, 1 lot of hydrogen-3, and the reactants are helium-4 and a neutron. So sum of the mass for the products is going to be 1 of these plus 1 of these, which is going to be 5.03, etc. Units or atomic mass units. Same thing for the reactants, and we can see there that these 2 values are different over here, and that is pretty much what we explained a little bit earlier, that the mass of the products is different to the mass of the reactants. In fact, the mass of the products will always be more than the mass of the reactants. So the question becomes, well, where did the mass actually go? Like, stuff doesn't just disappear, doesn't it? And so we get what we call the mass defect, which is the mass of the products less the mass of the reactants, which in this case is going to be 1.884 by 10 to the negative 2 atomic mass units. So that's kind of an introduction into the mass defect. And we'll have a look a bit later on as to where does this mass go and what's the importance of the mass defect. Okay, mass energy. So we know that matter can either be created nor destroyed. So where does this apparent contradiction fit in with our understanding of physics? That contradiction being that there's a difference between the mass. There is a mass defect. We also know that reactions typically give off some kind of heat or light or sound, but this is energy, it's not mass. So Einstein theorized that there was an equivalence of sorts, such that mass is converted to energy, and the opposite is also true, energy can be converted to mass. So that's our answer, pretty much, that his famous equation, E equals mc squared, explains where this mass goes. It works on the principle, E equals mc squared, of mass being converted to pure energy, which is light, or the release of photons. So what we'll find in a moment is that the mass that we had when multiplied by the speed of light squared gives us the energy of the light emitted from that reaction. Again, energy is in joules, mass, or in this case, for the previous example, mass defect is in kilograms. C is the speed of light in a vacuum. A quick question. Calculate the energy required or the energy released from a nuclear reaction that has a mass defect of 3.1 times 10 to the negative 29 kilograms. It's 1 mark. And then B, a Deuterium-Tritium fusion reaction results in a mass defect. Explain the relationship between the energy released in the reaction and the mass defect. You may include a formula to substantiate your answer. So there's 2 questions there for a total of 3 marks. So got about 3 minutes to answer that. So you can pause the video and click play when you're ready. Okay, now that you've had a go at doing the questions, or both of the questions, let's take a look to see how I would approach them. The first thing I'll do for part A is write down my formula, E equals mc squared. Simply substitute in the mass, which we have over here already in kilograms. So it'd be 3.1 times 10 to the negative 29 multiplied by c squared, and you get 2.79 times 10 to the negative 12 joules. Now for the second question, part B, I would write the following. So Einstein conceived the mass energy principle, which indicates that according to the relationship E equals mc squared, the mass defect of the reaction will be converted into energy in the form of light. Now, for those 2 marks, I would say that giving a formula and linking it to how the mass defect is converted to energy would give you those 2 marks. So it's a pretty easy question for 2 marks. And then, of course, I would then say, using that formula, that the mass defect is multiplied by 9.9 times 10 to the 16, which is the same as c squared, to give the resulting energy of the light in joules. Now, that's just going on to explain it a little bit more. Probably don't need that second point, but it's always good to add extra bits in to make sure you get the marks. Particles, antiparticles, and annihilation. So another application of Einstein's equation is to particle annihilation, which occurs when a particle, for example, an electron, comes into contact with its antiparticle. In this case, it would be a positron. Now, you may have covered this in 1-2 before, but if you haven't, pretty much what an antiparticle is the opposite of the normal particle, we can say. So it's got the same mass, but it's got negative properties. So the likes of charge, and then when you talk about quarks, they will have the opposite values. So when they come into contact, so a particle and an antiparticle, energy is released corresponding to the mass, the combined masses, obviously by E equals mc squared. All right, practice question 2. So in a hypothetical experiment, 1 gram worth of electron was annihilated with 1 gram of positron. Find the resulting energy released and the number of electrons annihilated. Remember that the mass of an electron is 9.1 times 10 to the negative 31 kilograms. So 3 marks, so you've got, let's say 3 minutes to do the question. Hopefully it takes you a little bit less than that, but you can pause the video now and click play once you're ready. Okay, now that you've had a go at question 2A for 3 marks, let's have a look to see how I would approach it. So the first thing that I would do is write down the formula. I tend to do this all the time, no reason not to do it in this case. Simply substitute in the mass. So here we've got the value of c squared, but here we've got 2 times the 1 gram, because remember, mass needs to be in kilograms, so it's going to be 1.0 times 10 to the negative 3 kilograms. But we've got 2 of them because it's 1 gram worth of electron and 1 gram worth of positron. 1 plus 1 is 2. Then we have simply evaluating that formula, we get 1.8 times 10 to the 14 joules. So let's just say now that the total mass is same as the mass of the electron multiplied by the number of electrons. Pretty straightforward. So we've got 1 gram of electrons, and we have the mass of one electron being 9.1 times 10 to the negative 31. Simply solving for n, the number of electrons, we get 1.1 times 10 to the 27. That's a lot of electrons. And this is why I have called this a hypothetical experiment, because realistically, we don't have the technology yet to do this. So that would yield the answer of being 1.1 times 10 to the 27 electrons. So in terms of mark allocation, I would give 1 mark for the energy, 1 mark for the number of electrons, because that's what it asks for, and then 1 mark probably for using the appropriate use of formulae. This is not really a formula, it can be just general understanding. So using E equals mc squared, finding the energy as a result, making sure that this is multiplied by 2, because there are 1 gram of electron and 1 gram of positron, and then we have the number of electrons. All right, now a pretty good question. Why can't we exceed the speed of light? And this kind of leads into our second part of this lesson, I suppose you could say. And the answer is as follows. So as our speed increases, the Lorentz factor, which we learned about a couple of lessons ago, also increases, and that increases towards infinity. As we approach relativistic speeds, our mass actually increases by m equals gamma m naught, or mass, the relativistic mass, is the Lorentz factor multiplied by the rest mass. Now, this may seem like a very superficial answer, and we'll see a little bit later, there'll be a graph a bit later that it kind of explains this a bit better, but pretty much all you need to know is that it would require an infinite amount of energy to reach the speed of light. And it's obviously impossible to have an infinite amount of energy, so we obviously can't reach the speed of light. The reason why we need an infinite amount of energy is that because as our mass increases, we need even more energy to accelerate it. Okay, let's have a look at relativistic momentum. So given that our mass changes when our velocity approaches the speed of light, so too must our momentum. And given that P equals mv, we can say that the momentum is actually gamma, or the Lorentz factor, multiplied by the rest mass, multiplied by the velocity. Okay, practice question 3. A spaceship travels at 0.999 c in a straight line. Given that the relativistic mass is 7.00 times 10 to the 5 kilograms, find the rest mass of the spaceship. 3 marks, so you've got about 3 minutes to do the question. You can pause the video and click play once you have completed. All right, now that you've had an opportunity to do that question, let's take a look to see how I would approach it. We have the Lorentz factor formula, which hopefully you remember, and if you don't, it is actually on the formula sheet that you get at the end of your exam. So gamma, or the Lorentz factor, is 1 on the square root of 1 minus v squared on c squared. Simply substituting in our v squared and cancelling the c's, because it'll be 0.999 squared multiplied by c squared divided by c squared in this bit over here. So we can, I'll write this down so that you can see it. So you can quite simply just cancel that, and you're just left with this value over here. And we get gamma is about 22, just more than 22, 22.366, and it goes on and on and on. Now, we also know that this formula from a couple of slides back, that the rest mass is our relativistic mass divided by the Lorentz factor. Simply substituting that in, and you get this value. You get 3.1297 times 10 to the 4 kilograms. Now, because we have 3 significant figures, we've got 3 there and 3 there, we can give our answer to 3 significant figures. So we'll write 3.13 times 10 to the 4 kilograms. Okay, the second part of question 3, hence or otherwise, find the momentum of the object under Newtonian mechanics. With 2 marks, so you've got 2 minutes to do this question. You can pause the video and click play when you know you are finished the question. Okay, now that you've had a go at that question, part 3b, let's take a look to see how I would do it. So the first thing I would write is that the momentum under Newtonian mechanics is going to be our rest mass times velocity. So the Newtonian mechanics refers to at low speeds. In fact, that's what we've learned also a couple of lessons ago. That would simply be our rest mass, which we got in the previous slide of 3.13 times 10 to the 4 multiplied by our velocity of 0.999 c. And you get that value, 9.38 times 10 to the 12 kilogram meters per second. Now, when it says hence or otherwise, you usually have to use your answer from the previous question, which is exactly what we've done here. We've taken this value from the previous question to find the momentum under Newtonian mechanics or Newtonian conditions. In terms of mark allocation, you'd probably give 1 mark for the answer, but also 1 mark for this step here, rather than a formula, because you need to substitute in your previous value. All right, using your answer from part 3b, find the momentum of the spaceship after relativistic effects are taken into account. So this now gives you an opportunity to get another 2 marks. So you can pause the video and get back to it once you are finished. All right, now that you've had an opportunity to do this question, let's take a look to see how I would do it. Now, the first thing I would note is that now we're finding the momentum when we take into account relativity, which we didn't in the previous question because it asked for things under Newtonian mechanics. So this is what we would describe as the more correct momentum because we're taking into account that we're traveling at high speeds, and so our gamma is going to be significantly more than 1. We also have to use our answer from part B. So we can say that our momentum is actually going to be the momentum from part 3b multiplied by gamma by this formula over here. So in the slide beforehand, we had P equals m0 times V. Here we need to multiply that by gamma, and that is exactly what we are going to do. So we get the gamma of 22 whatever it was, 366, and we multiply that by our previous answer, and we get 2.10 times 10 to the 14 kilogram meters per second. All right, so 3D, some more questions. Explain using the term Lorentz factor the answers given in part 3B and 3C, taking note of any differences between the 2 results. So this is with 2 marks. So you've got a couple of minutes, but because it's an explanation question, it takes you 2.5 minutes. You don't really have to worry. So you can have a go at this question, pause the video and click play once you are ready. All right, now that you've had a go at doing 3D, let's take a look to see how I would approach this. So I would say something along the lines of the 2 answers account for different understandings of the behavior of objects at relativistic speeds. So part B assumes that there's no effect on the mass as speed increases. So momentum is simply mass as it was measured at rest multiplied by the velocity. I would also say that part C assumes that the effect of the Lorentz factor changes the relativistic mass consistent with current observations of relativistic objects, such that the momentum is multiplied further by the Lorentz factor to attain the result. I've also included here this diagram, which kind of gives you an idea of the differences between what happens at speed. So this gives the momentum for an object of rest mass 1 kilogram, and both axes are in terms of c, the speed of light. So we can see here our answer is very, very close to 1. So our answer is actually going to be somewhere up here, because this line just keeps going down. There we go. close enough. And we also note the other thing that it never reaches c, the speed, because we can't. So the momentum goes up towards infinity, and there's a vertical asymptote at the speed equals to the speed of light. All right, relativistic kinetic energy. As our mass changes with velocity, so too must kinetic energy. So as our mass increases, it requires more energy to exert a force on the object to provide an acceleration. So therefore, we can say that it requires an infinite amount of energy to travel at the speed of light. So this is the formula for kinetic energy. It is quite simple, really, in that it is the total energy of the object. So it's going to be, that would be gamma m0 c squared minus its mass energy equivalence of the mass. So it's going to be gamma minus 1 m0 c squared. All right, so here we go. Practice question 4a. Calculate the kinetic energy of a spacecraft traveling at 0.99995 c and with rest mass of 1.0 times 10 to the 5 kilograms. Couple of marks, couple of minutes. You can click pause, and once you're finished, click play again. Okay, now that you've had a good chance to do that question, let's take a look to see how I would approach this. Pretty important, finding the Lorentz factor. We're going to need that, so simply substituting in the velocity there, and you get gamma equals to 100.0. We know that our kinetic energy from the previous slide is gamma minus 1 m0 c squared, which is quite simple to straight substitution. Here are the values, so you get your rest mass, pop that in with the m0, and you get this, that in there, and you get a gamma, which we pop in there. So you get 8.9 times 10 to the 23 joules. Last little bit before we wrap up, graphing using the Lorentz factor. So the Lorentz factor velocity graph indicates that a vertical asymptote at the speed of light. So we can see here it says 3.8, 3 times 10 to the 8, my apologies. And that means that there's going to be an asymptote somewhere along here. Exactly at 3 times 10 to the 8 meters per second. So it can be applied for a lot of things like momentum, energy, time, and length. And it gives us an understanding of what traveling at really fast speeds does to an object. So that pretty much is just a brief idea of what it would look like. They don't tend to assess it much, although it has come up in previous exams. All right, we have completed the lesson. So we covered a few things. We had a look at mass, energy, and E equals mc squared. A look at fusion reactions, particles, antiparticles, and annihilation, relativistic mass, momentum, and kinetic energy. And then we wrapped up with the graph of the Lorentz factor. So in our next lesson, which is going to be the final lesson for area of study 3, is actually a review lesson. But there is tons of stuff in there which you will definitely not want to miss. Loads of questions to test your knowledge. So thank you very much for your attention. Hopefully that you found the lesson interesting and that you learned something new. If you want to get in touch, feel free to go to the Air Learners page at airlearners.com, and you can find me on the tutors page. Thank you very much.